Hi, everyone. Thanks for tuning in. So let's start by taking a moment and taking a deep breath. Breathe in deeply and out. That felt good, right? Breathing is essential, but we rarely think about what we're actually breathing in. That breath, often taken for granted, contains countless natural and man-made pollutants that affect our health in many ways we don't always realize. In schools, where millions of students spend their days learning, these hidden threats are even more concerning. My project directly addresses this by designing a system to monitor indoor air quality. Hello, I'm Aneira Vundecode from Long Island, New York. My passion lies in engineering solutions to real-world problems, particularly those involving public health. Under the guidance of my mentor Omar, I developed a more accurate and calibrated system that monitors two key air quality indicators, which are CO2 and VOx. My goal is to create a system that schools can rely on to ensure healthier learning environments. So before diving into the technical details, let's clarify some key terms. IAQ, or indoor air quality, refers to the concentration of various pollutants in the air we breathe indoors. Poor IAQ can lead to headaches, drowsiness, and other long-term risks like respiratory diseases. It can also worsen pre-existing diseases such as asthma. CO2 levels, typically measured in parts per million, which is called ppm, are a good indicator of air quality, with levels above 1,000 ppm raising health concerns, as you can see on this chart here. VOx, or volatile organic compounds, are harmful gases emitted by products like cleaning sprays, solvents, nail polish remover, paint strippers, etc., and other household items. And on the bottom, we can see an average index of VOx from 0 to 500, with 100 being the average sort of indoor air quality reading. So monitoring CO2 and VOx is crucial as they can severely impact our well-being. Now, let's get into the heart of the system that I was able to develop. The Arduino Uno serves as a backbone of my design, connecting sensors that monitor CO2 and VOx. But what is an Arduino Uno? The Arduino Uno is a type of Arduino microcontroller that allows people to connect software and hardware components seamlessly and integrate multiple sensors like I have used. So in my system, I have a total of 5 different sensors and components connected to an Arduino Uno and a breadboard. These are namely the SGP40 VOx sensor, which can record VOx readings, the DS3231 RTC, which is a real-time clock module. What this does is collects the time that every single piece of data is collected in the system, so people can accurately see at what point what changes in the air quality are happening and can take informed action based on that. Next, I have the MG811 sensor, which is my CO2 sensor. This is an electrochemical sensor, which will give readings in ppm of the CO2 level in that area. Next, I have the TMP36 sensor. This is a simple temperature sensor, providing temperature in Celsius or Fahrenheit. And lastly, I have the microSD card adapter, which is the component that a microSD card can attach to, and this will basically collect the information that's being recorded from all the different sensors and components onto a microSD card, which can be opened on a data file, and I can then analyze and make informed decisions about the air in that area based on this data that has been recorded. So the data recorded on the micro SD card can be looked at for later analysis. And each component basically plays a key role in ensuring the system functions smoothly, as you can see in this diagram how all the pieces can come together. So here's a detailed schematic of the setup. Having this blueprint ensures the accuracy and reliability of the sensor readings by guiding and making sure I have the correct connections and voltage levels. As I said before, the CO2 sensor is an electrochemical sensor, meaning that it's performing chemical reactions in its sensor every single time it's collecting CO2 data. So it's also very important that all of these sensors and components are getting their accurate required voltage levels so that their readings are accurate. So precision is a key for a system like this where even small errors can lead to misleading results. So what sets the system apart from other indoor air quality monitoring systems? Calibration. In a study analyzing top 35 indoor air quality monitoring systems, only 16 included proper calibration or validation of the sensors that they used. Even fewer studies use an external reference instrument to verify accuracy. Calibration is vital, yet often overlooked. So I went a step further by not only calibrating these sensors thoroughly, but also cross-checking the CO2 sensor with an industrial standard vernier gas sensor, as we can see on the right. So what I did is where we see the two black lines, I induced a CO2 reaction of baking soda and vinegar and removed that reaction respectively. And as we can see from both sensors, there is a cohesive increase and decrease in both the sensors in proving that the setup is able to properly pick up these changes in the relative CO2 in the environment. And then for volatile organic compound sensor, I validated accuracy by using an acetone test in controlled conditions. And this rigorous approach ensures reliable data, which many systems fail to provide. At each of these black lines, I introduced a spray of an acetone solution above the sensor. And as you can see in the two sets of the three lines, those are each time there's a line that is one spray of the acetone solution, and we can see those steady peaks and then drops every time. That shows that the sensor is able to pick up these readings and is responding routinely similarly in a similar way to all these readings. So once again, this rigorous approach in calibration is something that's often overlooked, and which is why it's very crucial to ensure that when developing systems such as this, people are really going above and beyond and making sure that each sensor, especially when using Arduino sensors, are thoroughly calibrated and reliable, because this is data that's being used for something so important like indoor air quality monitoring. So we have to make sure we're getting accurate data. So what are some of the next steps? Well, looking ahead, I plan to enhance my system by integrating a Wi-Fi module, and this will enable real-time data to be streamed onto a web page. This would allow school administrators to monitor air quality live and take immediate action when necessary. So for example, there could be a sudden increase in the CO2 level in a room in a certain school, such as maybe a chorus room where students are singing for a whole period. And if the doors aren't open or there isn't proper ventilation, like there may be in some older schools like mine, this can be a concern due to all that buildup of CO2. So by the time the next group of students come in the next period, there's already a high level of CO2. So by being able to have this live demonstration of the air quality in these different rooms, school administrators can take informed, necessary decisions to make sure students are in a healthy environment, a really healthy and productive environment. So the goal here is to create a user-friendly solution that's scalable for schools and other institutions. And an example of doing this is by using the ESP8266 Wi-Fi serial monitor messenger component. So in conclusion, this project demonstrates the importance of monitoring indoor air quality, particularly in schools where health and safety are paramount. My system provides an affordable, calibrated, and validated solution that can be deployed widely to create healthier environments. It's not just about measuring CO2 and VOx. It's about making every breath students and staff take safer. Thank you for your time. Let's make every breath count.